We have all made it, sort of. Well, we made it, right? We're here. I made it because I'm a big Twitch star, but it's a different type of making it, so it's whatever. But, you know, you get the point. Why does something seem incredibly off? What do you mean? Uh-oh. Something is different, but I can't tell what. I don't know, dude. The camera is flipped? What? Isn't this how it's always been? Is it flipped from normal? Hold on. Let's do some research. Let's go back to the YouTube videos. Oh, you're right. You're right. Does it need to go back the other way? This is freaking you out. Should I change it? Please? Okay. Okay. Like this? Nope. Okay. This. That's so funny. I started using a different streaming setup so that I don't have to use my school laptop anymore because I hated doing it that way. And so now I just threw that in the trash and I can just purely use my desktop without needing to use my school laptop at all, which means I can use different streaming software. So I guess I didn't even notice, though, that when it was configured that I was mirrored. This way is actually weirder for me. I mean, I guess it's what I'm used to now. But for me, this is not mirrored. Right? Like, this is my left hand. Right? But for you, you see it on your right. So, but you know what? I'll make the sacrifice for my students. But okay. Let's go ahead and go through this then. All right, so let's just finish up 3 and 4 here. These are actually relatively shorter. There's not a huge amount. Hopefully you check these out. These are very doable overall. Okay, so number 3. Let R be the shaded region bounded by the graph of y equals natural log of x and the line y equals x minus 2 as shown above. Okay, part A. Find the area of R. Great. Come on. So just this shaded area in here. All right, without graphing, we should be able to know which of these is which line, right? So we should be able to determine this is the x minus 2, and then the upper line is the natural log of x. Okay, so I can definitely just at least make the basics of the integral. So I know it's the upper curve minus the lower curve. So natural log of x minus x minus 2 dx. So the only problem is I don't know what my bounds should be. I need to know where are these x values where the two lines intersect. So this is where we do need a calculator. All right, you'll either need your TI-84 or good old Desmos. Okay, so let me pull up Desmos here. I'm a genius and decided to type in these equations beforehand. I know. You're welcome. So here's that section. And on Desmos, again, if we hover over the points, we can click them. If you're on your TI-84 calculator, you'd have to do second, trace, and intersect. But in either case, we could figure out that these are located at 0.159, 3.146. So I'm going to put those on here. Zero 0.159, 3.146. Right, so we'll come back. And now it's just evaluating this integral. Which we can just type in, right? Math 9 brings up the integral, and we would get 1.949. Dunzo. Part A, easy peasy. All right, all of these part A's have pretty much just started off with finding the area between two curves. So it's always upper curve minus the lower curve. All right, so part B, find the volume of the solid generated when R is rotated around the horizontal line y equals -3. Okay, so there's some horizontal line here that we are rotating around. So whenever we do this volume of revolution, we always have to first decide, is this a washer method or a disk method? Well, we can clearly see the gaps here, right? So we're rotating around this line. But this area is not flush up against that line that we're rotating it around, which means there's a gap, which means we're going to have to use the washer method. Okay, so it starts with pi. From where to where, we're going to use our same bounds as before, because that's still where they intersect. 0.159, 3.146. And now slight difference. So like in the problem that we did yesterday, that upper bound, we're going to add 3 squared. Right? For the washer method, remember it's the outer radius squared minus the inner radius squared. Okay, but we have the +3 because this has to go an extra 3 down to y equals -3. Minus x minus 2, so the inner radius, but +3. Right, because we're rotating it around y equals -3. And it's all set up perfectly. So we calculate math 9, get about 34.198. And then lastly for part C, write but do not evaluate. So we don't even need to evaluate here. Integral expression can be used to find the volume of the solid. So we're thinking about rotating again. Rotating around the y-axis. Okay, so now I'm thinking about taking this. Ooh. And rotating around the y-axis. Right, well, since I'm rotating around, actually, let me come here. So first off, these were my 2 equations. So if I solve each of these, natural log, the way we get rid of natural log is do e to the power of. Right, or solving this equation, which is pretty difficult. Alright, so these are the curves that I then want to use. And I'm thinking about it in terms of y now. So if I kind of spin that, if I'm just looking at it in terms of the y-axis, now that straight, that linear curve, that linear function is now sort of the outer curve, right? Because if you turn your head and look at this on the side, that green line is now kind of the top, right? And then the actual curved part is the bottom portion. So when I set this up, right, to find this volume. So the pi on the outside, that stays the same. All right. And y plus 2 squared, right? Because again, like I said, the linear function is now the outer term. I solved this first equation. Y equals x minus 2. All right, that was the original function. Y equals x minus 2, so I just added 2 to both sides. Yes? No? Okay, minus the inner curve squared, right? Because that's what we do with the volume of revolution. Outer curve squared minus inner curve squared. And we're using the washer method again. Because look at all this space in between the shaded region and the y-axis. So we have to use the washer method. Okay, now the question is, what are my bounds? So we don't want to use our same bounds as before because those are x values. Okay, well, good news. We have an equation that if we know the x value, we can then figure out what the y value is. All right, so it's kind of like when we do u substitutions, we have to change the bounds over to u. Well, let's change our bounds from x values to y values. So y equals, what was our lower bound? 0.159. Okay. I must have thrown my calculator in the trash can. I don't know where it went. Maybe I did it when I threw my laptop. Oh, here it is. 0.159 minus 2. So that's negative 1.841. Right, that's my lower bound. And then my upper bound. So if I take the upper bound, which was 3.146, minus 2. So, I guess that one I don't need to do. 1.146. Okay. 1.146 upper bound, negative 1.841 lower bound. And then I need my dy on the end since all my equations are in terms of y. And we just integrate this, right? Math 9. Or actually, no, we don't even need to integrate it, do we? Oh, gosh. I'm working on my writing. Again, like I said, I got a new setup, so I don't write on my laptop screen anymore. I have a different surface to write on, so I'm practicing with it. I know my handwriting's pretty garbage anyways, but if it looks even worse than usual, it's because I'm trying to get used to this. Right, but part C just said we don't need to evaluate, just need to write an integral expression. So we're good here. This represents that volume of revolution. But since we're revolving around the y-axis, then we have to make sure that our integral is in terms of y. So that's why we had to change our equations and change our bounds. Ooh. Okay. All right. Cool. So let's go on to number 4. Let R be the region bounded by the graphs of y equals sine of pi x and y equals x cubed minus 4x, as shown in the figure above. We should put the performance task memes into the lead showcase night. We'll have to we'll have to do that. I'm sure it'll go well. Isn't the lead showcase night just going to be like a Zoom meeting? So we'll all just join the Zoom meeting, and then we'll just make our screens the memes. Everybody just has a different meme, and that's what you make your screen. So throughout everyone can just see random memes. Yeah, I'm still showing the memes at the end. Gotta save it for last. Yeah, I saw RJ. I got it. Hexers. Okay. Area of a shaded region between two curves. Outer curve minus the inner curve. All right, so we have to decide which one is this upper curve. Is it the sine function or is it the cubic? Okay. Just from our familiarity with functions, we might be able to determine that the sine function is the upper curve. If you're not positive, then that's okay. Just graph it. Okay, so I was going to pull up the graph anyway, so let's pull up Desmos because we love it. Let's get rid of those. Sine to x cubed. All right, and compared to our function, all right, so it looks a little bit different, but it's this area right here where my mouse is, right? This is the shaded region that we're talking about, right? We can tell it goes from 0 to 2, just like on the graph that we see. And I can tell that the sine function is the, right? So the top function, sine of pi x, minus bottom function. I don't need to square these. Okay, the squaring is only if we're talking about revolving around a line or an axis. This is just straight up find the area between, okay? Oh, oops, I need my bounds. So let me go back to Desmos. Again, if you're on TI-84, use second trace intersect. If you're on Desmos, okay. This one is also pretty easy. You could tell just by looking at the graph that it's from 0 to 2. All right, it's not a very tricky graph. It puts it straight there. We can see that 0 and 2 is where this starts and stops. But, you know, it's okay to be certain. So 0 to 2. And we could do this by hand. All right, sine of pi x, not crazy difficult to do. X cubed minus 4x, that's just power rule for integrating. Because I guess why not? It would just equal 4. -2 splits the region into two parts. Write, but do not evaluate, an integral expression for the area of the part of R. It's this line. And we want to know what is the area of this shaded region specifically. Okay? So let's set up the integral at least as much as we can. So area of a region, outer curve minus the inner curve. Right? or top, I guess top curve minus the bottom curve. All right. Okay, hold on. Let me pull up my Desmos again. So that I can figure out what are these points of intersection. Right? What are those x values? Because we need them for our bounds. And 1.675. Those are my boundaries. And then -2 minus x cubed minus 4x dx. And it tells us we do not actually need to determine the actual value. It just says, kind of like our last problem did, right? Do not evaluate. It just says write the integral expression. So that's all we need to do. All right, let's look to part C. The region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Find the volume of this solid. All right. I'm going to erase this so I can draw on. This is the stuff that you really love that we talked about yesterday. Okay, so what this is saying, again, this shaded region I am looking down at straight on. Okay, you are a bird flying over this shaded region that is the ground. Right? And the cross sections that are made are squares. That's what the problem tells me. So if I look at one of these, so this is going to be harder to draw. Let's try on the smaller piece. Maybe that would be. That looks perfect. Okay. So again, those dotted lines, those are coming out of the screen directly at you. Okay, so you're looking down at this shaded region. If you put your hand down to touch it, you would touch the top of it, which is a flat surface. The sides are flat surfaces. It's just that it's okay in this kind of curved shape. I guess not flat surfaces for the sides, but it's smooth. Right? Smooth shape. Get rid of that page. Okay. So my first question is, for these red solid lines, not the dashed lines, what is the length here? Right? Because in order to know the area, when we're doing volume of a cross-section, right, volume using cross-sections, basically we're just saying take an area formula and integrate it. Okay, so we're thinking about the area of a square. Right? Well, that's just the sides squared, right? Length times width, but the length and the width are the same. So, right, same thing for any square that I draw here, but that's exactly what this is, right? The upper area of this square So this is, wait, I already forgot what it was. Sine of pi x. Oh no. Sine of pi x minus x cubed minus 4x. And then that's squared because, right, the length and the width are the same. Toothpaste break. Yeah, mods, please ban. So then to find the volume, that's just the area formula integrated from the certain x value. So it's just the area. So this same exact expression, I'm just writing again. Sine of pi x minus x cubed minus 4x. The bounds. Right, this goes from 0 to 2. Math 9 to do the actual integral, we would get 9.978. All the volume of the cross-section problems is you take an area formula, and we want an infinite amount of areas, infinite amount of slices. So that's why we use the integral. So we just integrate over the area formula for volume of by using cross-sections. All right, part D. The region R models the surface of a small pond. Great. At all points in R at a distance x from the y-axis, the depth of the water is given by h of x equals 3 minus x. Okay. Find the volume of water in the pond. Interesting. Okay. All right, so now what we're imagining, get rid of this stuff. Okay, so still imagine, you're a bird flying over this shaded region. You look down, you see that shape, but what that actually is the shape of a pond. All right, so you're flying straight over this pond. Okay, and a pond, the bottom of the pond is different heights depending on where I am, right? Which is, somewhat true to real life, that, the bottom of bodies of water are not just one specific depth. Okay. And we have, this is the formula for figuring out the depth. All right, well, let's first think about then, if I want to know, wait a second, oh, come back, oh. Okay. All right, so this is a similar idea where we're trying to do like an area integrated over an infinite amount of slices. Right, so it is still true, right, if I want to think about my rectangles or whatever, between those two, between the top of the pond and the bottom of the pond, and I guess that's not really a great way to describe it, but between, here and here, the distance between there is the upper curve minus the lower curve. All right, so I'm still thinking about this. Okay, but then my question is, how deep does the pond go? Right? I don't know how deep it goes, but we do know that we have a formula now that represents that depth. Right? We were told that depth is what? 3 minus x. Out of the screen as we're thinking about going into the screen because we're thinking about it as a pond. Okay, then that depth will be 3 minus x. So the area of this, it won't be a square anymore, but rectangle is 3 minus x. So this is my length. Times 3 minus x, the width. And then we want to take an infinite amount of those slices. So we'll integrate it from 0 to 2. And then dx. And from here we're good to go. We'll math 9 it. And we get 8.369. The expressions for C and D are so similar. Here we had this, which represented the length between the two curves, and then we squared them because our cross-section, what we knew was a perfect square. The problem told us that. So this side and this side had to be exactly the same. But now it tells us, okay, it's not a square, but the height or depth is given by this equation. All right, well, that's fine. The area formula is still just length times width. So this is the length. This is the width or the depth of the pond. And then integrate it across the entire dimension of the pond from 0 to 2. This is what we get.